Alrighty, my friends, in this video you'll learn how to solve for the entropy change or the reaction entropy using the products minus reactants formula right here. And I'm going to do that using real exam problems. And this is geared towards a general chemistry class in thermodynamics. So we won't use any calculus here. Okay, so this is our first exam problem here. Calculate the entropy change or the reaction entropy, either or, we could say that, for the following. And we have part A and part B. So part A, I'm going to just move this down a bit here to give us some space. Okay, and get rid of the cursor. Okay, so to solve this, we're going to use, and this superscript, see this superscript? This superscript means it's at standard conditions. So 1 bar. 1 bar is what this superscript means. It doesn't, we don't know what the temperature is, but it's usually 298 Kelvin. So to do this, we're going to use the formula, which is products minus reactants. So the entropy change of the reaction, standard entropy change of the reaction, is going to equal the sum of the entropies, and these are the molar entropies, usually you have an M there, of each product, and each product is going to be multiplied by its stoichiometric coefficient, so like there's a 1 here, and if there's another number, that would be a stoichiometric coefficient, times the sum of whatever the stoichiometric coefficient is, 1, or in this case it's 1/2 for oxygen, times the molar entropy of the reactants. Okay, and to do this, we got to look at a table of values to see what these molar entropies are because they need to be measured. Oh, that's the calculator. We don't want the calculator. So we have the molar entropy right here, and we need SO3 for the product. So I'm just going to do a search, SO3, and we got to make sure it's in the right phase. This is in a gas, so SO3 in a gas, the molar entropy in joules per Kelvin mole is 256.76, so 256.76, 256.76, and this, the stoichiometric coefficient is 1 because there's a 1 there. Don't have to include it, but that's okay. And that's joules per mole Kelvin. Okay, minus, and after this minus, always give yourself a big bracket here because you don't want to miss out on distributing this negative sign into the various terms. So for the first one, it's going to be the stoichiometric for SO2, which is just 1, times the molar entropy of SO2, which is right above it. That's convenient. And that's 248.22. So 248.22 joules per mole Kelvin, plus, because we're doing a sum of the molar entropy for oxygen, now we have the stoichiometric coefficient, and it's not 0. It's 0 for the enthalpy, but it's not 0, so you don't want to kind of mess that one up. Where's the O2? Oh, there's 11 things. Let's say O2 gas. Here it is, right above it. So, I did O gas, O2 gas. Now I got to find it again. There we go. So it is 0 for the enthalpy, and it is 0, thus enthalpy of formation, and 0 for the Gibbs energy of formation, but it's not 0. This number is never 0 for substances at 298 Kelvin for the molar entropy. This is something so always just go to the table rather than use your gut, maybe, unless you already know that. So molar entropy is 205.138. So 205.138 joules per mole Kelvin. And we'll close the brackets. Okay, now we'll plug this into our calculator. 256.76 minus bracket. I won't include the 1. 248.22 plus 0.5 times 205.138. Close brackets. Looks good. Negative. Okay, so negative 94.029. Negative 94.029 joules per mole Kelvin. And how many sig figs do we have? 2 decimal places, 3 decimal. So we only have 2 decimal places of significance here. So negative 94.03 joules per mole Kelvin. It's negative, which means entropy is decreasing. the reaction entropy is decreasing, which makes sense because we're going from a higher number of moles of gas, kind of for every 1.5 moles of gas that react, we only get 1 mole of product. So we're decreasing the number of moles of gas, so decreasing the number of arrangements of the molecules, or if you think of the number of microstates, or kind of the disorder is kind of decreasing because we have now 4 atoms bonded together per molecule rather than kind of less for the reactants. Okay, so now we'll do the next one here. And if you're stuck with me, that's good because there's some important parts here that I didn't cover in the first question. But we will set it up as before. So we have the sum of the coefficients times the molar entropies of the products minus the sum of the molar entropies of the molar stoichiometric coefficient, molar entropies of the reactants. Okay, now unlike equilibrium constants and things like that, we need to consider all the species here in the entropy. So even all the solids and the liquids and whatnot. So we're going to start off with hydrogen. So there's 3, that's the stoichiometric coefficient. Now we need to look at H2 gas. Where did it go? There it is. So it is 130.684. So 130.684 joules per mole Kelvin plus 2. Now the aluminum chloride, it's in an aqueous form. So this is super key. Make sure we're looking at the aqueous one, AlCl3. Oh, it's not here. So okay, so I looked at online. I couldn't really find a good table for it. You would be given the entropy, but I did find it here on this website. I'm not sure how accurate this is, but we're going to use this number. Okay, so AlCl3 aqueous is negative 148. Again, we lose some precision, but oh well, negative 148 joules per mole Kelvin. So we'll plug that into here. Negative, yeah. Okay, negative. Oh, that's okay. Yeah, so negative is just, I mean, we have this compound here, so it doesn't have to be positive. Negative 148. Doesn't have to be positive because it's existing in solution, right? Not just as it is. Negative 148 joules per mole Kelvin. So we'll just kind of borrow that number. And, oh, that's not it. That's our product. So we need to minus the reactants, and we want to have a big bracket after this minus. So we have 2 times the molar entropy of aluminum, which is 28.3. Again, it's not 0. 28.3 joules per mole Kelvin plus the HCl, 6. Now, what's HCl? Now, we want to aqueous, right? HCl aqueous right down here, the right phase. It is 56.5. So 56.5 joules per mole Kelvin. Alrighty. Okay, so we'll plug that into our calculator. We don't need that number. 3 times 130.684 plus plus 2 times negative 148. Close brackets, minus big bracket here, 2 times 28.3 plus 6 times 56.5. And I think our brackets look good. Yep, so negative 299.5, negative 299.5 joules per mole Kelvin, although we only have precision to the ones place value because of this one right here, the AlCl3. So we'll say it is negative 300, and that decimal there to say that we have 3 sig figs, joules per mole Kelvin. All right, next one here, last one, and we're getting a little bit more complicated. So this is more like an exam problem, kind of a harder exam problem-ish, I guess. Find the entropy change if 3.14 moles of potassium, to be chlorate, react as shown below, and we're given this balanced equation. So now we want to know the change in entropy, not for the reaction per mole, kind of per mole of the reaction. We want it for this many moles of KClO3. So we're actually going to calculate the entropy change of the reaction as is, just like before. So we're going to sum these all up. So that'll be 2 times whatever the molar entropy of KCl solid is. So KCl solid, 82.59. So 82.59 joules per mole Kelvin, plus 3 molar entropy of oxygen, which we just did, but I don't remember it. Not that one, not that one. This one, it's a gas. Okay, so 205.138. So 205.138 joules per mole Kelvin, and minus the reactant. And we don't need a big bracket here because there's just one reactant, although you might want to include it just so you make sure you don't forget it, of KClO3, KClO3 solid. That's good. That's what we have here. 143.1. So 143.1 joules per mole Kelvin. All right, so we're going to solve for this. And again, this isn't our answer, right? This is our halfway step, and I'll explain why this isn't our answer once I get through this. 85 plus 3 times 205.138 minus 2 times 143.1. Okay, so 494.394. Oh, 494.394. That's neat. 494.394 joules per mole Kelvin. And we have 1 decimal place of precision because we're adding them up. Now, this per mole is per mole of the reaction. Okay, so if 2 moles of KClO3 reacted, we would, to give us 2 moles of KCl and 3 moles of O2, this would be the entropy change. So this per mole is per mole of this reaction. Okay, we want to know how many there are for 3.14 moles of KClO3. So this is not moles of KClO3. This is moles of the reaction. So if we want the molar entropy change of, the molar entropy change of KClO3, we got to divide it by 2. So we got to take, I'll show you the math, 494.394 joules per, and I'm going to say, I put the Kelvin here, and this is per 1 mole of the reaction, which is 2 moles. Actually, I'll change that to 2 moles of KClO3. I hope you can see that. I hope this is clear when I do this. So this is per mole of the reaction, and for every time a mole of this reaction occurs, 2 moles of KClO3 react. I hope that's clear. Let me know if that's not clear, but I hope that's clear. That's this many joules per Kelvin of this many moles of KClO3. Now, we don't have 2 moles of KClO3. We have 3.14 moles. So we're going to multiply this by pi. Just happens to be pi. 3.14 moles of KClO3. And that gives us something. Let's see. We got that number there, so all we got to do is multiply it by 3.14 and divide it by 2. 766. We only have 3 sig figs. This number 2 is an exact value, so 776. Yep, that's it. Final answer. So 776 joules per Kelvin. This wouldn't be the molar entropy then at this case. This would just be the change in entropy for this many, for 3.14 moles of KClO3.